Hi class, back to linear algebra. We're going to be talking about type 1 matrices, which is a type of elementary matrix. Generally, this is what they do and this is what they look like. A type 1 matrix will exchange row I with row j, and it will look like something like this. It will kind of look like an identity matrix, but in the ith row, it will have a 1 in the jth column. And in the jth row, it will have a 1 in the ith column. It will have zeros elsewhere. So a type 1 matrix that exchanges rows I and j is basically derived from an identity matrix, but then you exchange row I and j of that matrix. What we're interested in is finding the determinants of our elementary matrices. So let's look at claim 14. If E1 is an n by n elementary matrix of type 1, and A is an n by n matrix, then the claim is that the determinant of E1 times A is equal to negative of the determinant of A. Left multiplication by a type 1 elementary matrix will negate the determinant of a matrix. Before we prove this, let's actually think about the idea of how it's going to be proved. Here's the idea. Say we've got a matrix A, B, C, D, E, F, G, H, I. And E1 is going to be the elementary matrix that exchanges row 2 and row 3. So this is going to be A, B, C, G, H, I, D, E, F. What we're going to do is we're going to expand along an unmoved row to find the determinant. In this case, the unmoved row is the top row, so we'll start from A and go left to right. So in the expansion of the determinant, we're going to take A as our coefficient, then ignore the column and row that it's in, and we're going to multiply by the determinant, or either positive or negative multiple of the determinant of this matrix that's left, which is M11 in A. If I were going to do the same thing in E1 times A, I would start here and I would ignore the column and row that A is in, and then multiply by the determinant of the matrix that's left. This matrix in notation is M11 of the matrix E1 times A. Notice the relationship between M11 and A and M11 and E1 times A. It's simply the same matrix, but with the rows exchanged. And in particular, because of this, the determinant of M11A, we can just calculate it in this case, is going to be negative times the determinant of M11 in E1 times A. This is the main idea of our proof. So let's prove it. First, by writing out the full claim. If E1 is an n by n elementary matrix of type 1, and A is an n by n matrix, some other n by n matrix, then the determinant of E1 times A is going to be negative the determinant of A. This is just basically saying exchanging rows negates the determinant. As a consequence of this, we actually have an additional part of this claim. Therefore, the determinant of the matrix E1 itself is -1. Let's prove it. Proof. We will do a proof by induction. We're going to induce on the size of A, so we're going to induce on n. The elementary matrix needs to exchange rows, and so n has to be greater than or equal to 2. Therefore, our base case is in the n is equal to 2 case. For 2 by 2 matrices, there's only one possible matrix that will exchange row 1 and row 2. It's this matrix, 0, 1, 1, 0. And say A is some other 2 by 2 matrix, A, B, C, D. Then, let's look at the determinant of E1 times A. This is simply the determinant of the product of these two matrices. Let's just work it out. This is the determinant of CD, AB, which is BC minus AD. This is negative times AD minus BC, which is the negative of the determinant of the matrix ABCD. ABCD is A, so this is negative the determinant of A. Thus, we've established the base case. For our inductive hypothesis, we're going to assume this holds up to K by K matrices. And then in our inductive step, we will prove that it holds for n is equal to K plus 1, as in K plus 1 by K plus 1 matrices. Just like in the idea of this proof that we explored before, we're going to expand along an unmoved row. Why do we know that such a row exists? This exists because n was greater than or equal to 2 to start, so n is equal to k plus 1 has to be greater or equal to 3. Now let's work through it. The determinant of E1 times A is going to be the sum of aik negative 1 I plus k times the determinant of mik in the matrix E1A as k ranges from 1 to n. Remember what we learned from the idea about this determinant. This is going to be all of this times negative the determinant of mik A. Add some more parentheses here. We're going to take this negative sign all the way out to the front as a negative 1. And what's left is aik, negative 1 to the I plus k, times the determinant of mik A. And this is negative 1 times the determinant of A. Now let's look at the additional claim. We're going to use what we've just proved, but for A is equal to the identity matrix. This is how we're able to say that the determinant of E1 is equal to the determinant of E1 times the identity matrix, since the identity matrix times any other matrix is the other matrix. This is -1 times the determinant of I by what we just proved, and we know that the determinant of I for any identity matrix of any size is 1. End of proof. QED. Let's do an example. And yes, I admit that this is a little bit contrived. Say I've got A is the matrix 0, 2, 3, 1, 8, 1, 0, 0, 5. I could do this directly, or I could use some of the claims that we've been establishing. So let's look at 1, 8, 1, 0, 2, 3, 0, 0, 5, a different matrix. This different matrix is triangular. So in order to calculate the determinant, all we have to do is multiply the diagonal entries. 1 by 2 by 5, this is equal to 10. We'll notice that this new matrix is obtained from A by simply exchanging two rows, as in it's been multiplied by an elementary matrix of type 1. We know what this does. This negates the determinant. So we can conclude from this that the determinant of A is equal to -10. Here's an exercise for you. Find the determinant of A equals 0, 1, 0, 0, 0, 1, 1, 0, 0. Do not do this directly. Do this by seeing how many row exchanges are needed to get the identity matrix. Then use what we know about the determinant of the identity matrix and claim 14. Next, type 2 matrices. See you next time.